Hello everyone and welcome back to Causality with Boris, all broadcast from SobolevSpaces. In this video, I'll talk about how conditioning variables define strata. There are three main topics in this lesson: graphical presentation of conditioning, strata in Pearl's formula, and pooling strata effects. Make sure you watch till the end and compare the takeaways with your notes. As always, I have prepared a PDF that goes along with this video. Check out the link in the description and the PDF will be sent to your inbox. Ever wonder how conditioning would look like graphically? This is the moment to find out. And I will use our recurring example of the treatment timing. Take a case of heart disease. Is it appropriate to recommend surgery that is likely to be delayed if alternative treatment, angioplasty, can be performed sooner? We are of course talking about patients who can have either treatment. The answer is unclear. Heart surgery is done to alleviate chest pain and to delay myocardial infarction. But there is a time between decision to operate and the operation itself. And that's our concern here. You see, longer times may lessen therapeutic benefit. And how long is too long? Well, surgery is delayed if it's done after clinically appropriate period. So we compare surgical outcomes between two study groups, early and delayed surgery. Let's take a look at this dependency graph. It shows forces that shape the relationship between surgical timing and post-operative mortality. Known factors and their dependencies. Arrows are the direction of dependency. We color nodes based on Pearl's taxonomy. The green nodes are factors that influence only surgery timing. Red nodes influence both time to surgery and its outcome. And their influence is direct or indirect. The green arrow is the mortality effects of timing and the red arrows show non-causal paths. The following figure shows a modified graph. I removed all arrows that were coming to and from the orange nodes. These are calendar period, type of admission, age at admission, and presence of other illnesses. These are the factors that influence both timing of surgery and the occurrence of death, indirectly through the chain of dependency. Conditioning on these factors blocks all the paths that may produce covariation between time to surgery and its outcome. How conditioning could be shown graphically? Yes, by removing all arrows coming in and out of these factors. But more telling is the disappearance of all non-causal paths. What does it mean for the causal analysis? Well, we see no non-causal paths, then we can identify the effect of timing by comparing average outcome in timing groups for every combination of these conditioning factors separately. Suppose combinations of variables define a set of strata. For instance, combinations of age, admission type, coexisting conditions, and the treatment period create 36 multifactorial strata. We then find the difference in expected outcome between treatment groups, and that's done within each stratum. Then we apply the Pearl's formula. The overall treatment effect will be the sum of stratum-specific differences, weighted by the strata prevalence in the study population. Here, if stratification variables meet the backdoor criterion, then the difference between marginal means is attributable to the treatment group membership. Pearl's formula links outcome probability to conditioning variables, but it doesn't specify an exact formula for the link. It just says the outcome probability given conditioning variables. Ideally, we wouldn't need a formula at all. We could find these probabilities from data, simply by estimating sample means for each treatment group within each stratum. Here is the problem though. It may not be feasible when there are many strata. We may not have enough data. And before resorting to regression modeling, let's take another look at Pearl's formula. It doesn't say anything about how strata are defined, or how they are supposed to be defined. It doesn't say only combinatorics will do it. In fact, the formula is completely agnostic of strata definition. The formula works for any rule that links two things: a set of conditioning variables and the list of strata. Any mapping of multidimensional space of variables on the set of countable things. It could be a list of telephone numbers or your grocery list. Anything that's countable. You can see it for yourself in this equivalence formula, whether we use categorical variable s with the distribution of its value or the joint distribution of multiple variables, the averaging will produce the same result. We just realized that strata could be defined by various rules. For instance, this table shows 6 strata. They were found by the variable partitioning algorithm. It's available in many software applications. We use the same 4 conditioning variables, and we end up with 6 strata, instead of 36 resulting from combinatorics. The beauty of stratification is in simplicity of aggregate data we need. This table shows counts and proportions across the strata. Counts of surgery, counts of outcomes, and the proportion of outcomes in timing groups and in strata. That's it. If treatment effect varies across strata, we're looking for an average over strata prevalence in the study population. The forest plot is another way to present the effect variability. At first, it was used for meta-analysis of randomized trials, multiple trials concerned with the same question. In the last 20 years, forest plots came to observational studies. There, they are often used to present a subgroup analysis. That's how the plot looks. The squares in the plot show risk differences, one for each strata. Their size is proportional to strata weights used in the analysis. The diamond shows the summary measure of variation, the pooled effect. Lines on both sides of the diamond reach to confidence bounds. We check if the confidence interval overlaps with a vertical line running through 0, which indicates no effect. Computing the average treatment effect is conceptually similar to pooling effects in a meta-analysis. The only difference lies in the approximation of confidence intervals. The random effects model is a common choice for averaging because it doesn't assume the same effect across strata. It's simply the average of sample means. The pooling formulas work well for risk differences, but not for the odds ratios. When outcome is binary, we express treatment effects through difference between marginal risks. Alternatively, it could be odds ratio. How do we find the marginal odds ratio? We can't average odds ratio from strata, so we don't pull it from the strata effects. Instead, we compute marginal odds ratio using marginal risks. First, we calculate marginal probabilities for each treatment group. They are P1 and P0 here. And we compute them by averaging stratum-specific outcome probabilities. Then we enter their values into the odds ratio formula. Recall, it's a ratio of 2 odds. And what are the odds of the outcome in the treatment group? It's P1 divided by its complement. And what are the odds in control groups? It's the P0 divided by its complement. Easy. However, the standard error of this estimate is not easily available. Let's go back to the cardiac example. Surgery outcomes by its timing. This table shows strata-specific outcome probabilities, and we see a substantial variation from 4% among patients from the early period who were older and had non-urgent admission in the delayed surgery group to less than 1% among younger patients in early surgery group. We find that marginal outcome probabilities in the timing groups are different, 13 and 10 deaths per 1,000 surgeries. Early surgery is an intervention here, it corresponds to P1. So here is the total treatment effect. If all patients had access to early heart surgery, then there would be 4 fewer deaths for every 1,000 surgeries. We take the odds ratio formula. Plug in the known values for P1 and P0, and we get the value of 0.73. That's the effect size on the ratio scale. It shows the number of times odds in one population are smaller than in another population. Therefore, if everyone had surgery within clinically appropriate time, then the odds of postoperative deaths were only 73% of that if every patient was delayed. With all the cancellation of planned surgeries due to the pandemic, it's not a hypothetical scenario anymore. So here is the main message. The adjustment formula doesn't specify the link between the outcome probability and conditioning variables. You learned that conditioning variables can define strata in many different ways, not only by their combinatorics. You learned how to use aggregate data and forest plots to communicate stratification and averaging. You might have seen forest plots in meta-analysis of randomized trials. Recently, they've been repurposed for the subgroup analysis in the observational studies. You also learned about the pooling effects in meta-analysis and its similarity with averaging in stratification. Keep on watching.